Hi everybody, welcome to a new video. In this video we are going to see how to create a particle system with an emitter and particles with a specific lifetime. So the particles will start from a specific point, they will follow certain physical rules, let's say, and then they will die and so disappear and come back to the position of the emitter. So, for example, a practical example of that is this video. In which the particles start from a certain position, which is this sphere here. And then the particles follow a certain trajectory, so they are subjected to certain forces and they go into a certain direction. And then when their lifetime is over, they come back to the sphere in the initial position. Okay, so we're going to see how to create this mechanic inside Max using, of course, Gen. Okay, so let's start. First of all, we need, of course, our JIT world and the camera. Camera is not strictly necessary, but I just like it to have it because we can move around with the camera using JIT anim drive. So it's pretty nice. Then another thing that we need is a JIT noise to give us the initial position of the particles. So let's make it float 32, 400 by 400. This is 160,000 particles. So 400 by 400, it means we will have 160,000 particles. Let's create a load bang here. And this will be our initial position. So this is the initial position. Then what we need is a JIT matrix, which we will call pos, also three planes because we need to deal with x, y, and z position. Every one of these coordinates will occupy a single plane of a cell of this matrix, so we need a matrix with three planes. So 3, of course, also float 32, 400 by 400. And this position matrix needs to be continuously banged. So this is the method that comes out of the middle output of the JIT world object. This matrix needs to be continuously banged out because we need to continuously update the position of the particles. Then let's create a JIT gen. Oops. JIT gen. Let's give it a title. Let's call it system, for example. And then let's create a jit.gl mesh. Game is the name of my JIT world here. Let's set the draw mode to points and the color to white. Okay. So when we do this, we bang that, we can see that a cube of points has been created. All these points are in between the position 0 to 1 on every one of these axes because of the JIT noise object. Okay, so what we need to do now is to create another matrix called again pos. So this is the same matrix as this one, and we attach this here. So basically this means that the position of the particles will be transformed inside JIT-gen, will be output inside this matrix that has the same name of this matrix here. And so in this way we will create a feedback loop in which then we can work with the new position of the matrix, of the particles. So let's say this is the old position, and that's the new position after being worked inside JIT-gen. Okay, so let's go inside JIT-gen and see what we need to do here. First of all, we need to calculate a force that will drive our particles. So first of all, let's say that our particles are subject to gravity. So simply to gravity. So we need to calculate a force that pushes them toward the bottom of our window. Well, that's fairly easy. We just need to subtract to the position a certain vector. So in this case, since we want that the particles go toward the bottom of our window, we have to create a vector which has a 0 on the x, because we don't want to subtract anything on the x, a very small quantity on the y, and 0 also on the zeta. So in this way, oh no, sorry, this must be actually positive because we are already subtracting. So if we bang this here, you can see that the particles start to slide toward the bottom. And they will slide indefinitely toward the bottom if we don't do anything to prevent it. So they will go just down and down and down. But we can prevent they to disappear from the screen by using a wrap object -1, 1, which will wrap any plane of this matrix in between the numbers -1, -1, and 1. So every number that comes from this operation will be never greater than 1 and never less than -1. When this is less than -1, for example, so when the particles are here at the bottom, they will show up again here at the top. So let's see if they show up again. Yeah, you see they coming back. Let's load bang again. And now we can see that the particles, once they arrive to the bottom, then they come back from the top. And this is how we can prevent them from disappearing from the screen. Okay, now you will have noticed that every one of these particles has basically falls at the same speed, because of course they are all subject to the same force. One way to make this more interesting is to give a mass to every matrix, to every cell, sorry, to every particle. So in order to do that, let's create another JIT noise. Let's call this mass. We don't need 3 planes, we just need 1 plane here. And let's also bang it at the beginning. So we need 1 plane here because this is a number that we are going to multiply for the force applied to the single particle. So let's switch anyway x, even if all the 3 planes are now the same. This is now 3 planes because when coming inside the JIT it will get the same dimensions and number of planes as the most left matrix. So this is now 3 planes. We will switch one of these planes just to be sure that the number is the same for every plane. And then we multiply this force by this number, which goes from 0 to 1. So in this case, it can just be less than the original number, or can at most can be the same number. So you can see now that the particles are falling with different speeds. Some are not falling at all because probably the number is too small. So let's add a plus 0.1 to that number just to make sure that we never multiply by 0 and the particles are always subject to some kind of force. So you can see now that particles are falling with different speeds. So that's pretty nice. And actually, let's do something with the initial position. Instead of having it between 0 and 1, let's actually make it between -1 and 1, so we can occupy already a cube that goes from -1 to 1 instead of going just from 0 to 1. So let's get to this jit.gl title. Let's call it signer. So inside here, what we want to do is simply to multiply the noise value by 2 and then subtract 1, so we are now in the range -1 to 1, okay, because when we multiply by 2 is the range 0 to 2, and then if we subtract 1 to then the range will be -1 to 1. Okay, so let's mang again, and we have our cube. that is now centered in the center of the world. So what we want to do now is to actually store the velocity that these particles had in the previous frame and use it in the new frame in a way that the velocity can be summed and can basically become an acceleration, because we are continuously summing the velocity from the frame before, and the particles kind of accelerate. So in order to do that, let's create again another matrix with a name. We will call this bell. And this method here, let's create a trigger. Let's put 3 bangs because we will need another one still. And let's use the second output here for this velocity matrix. And we also need to copy this matrix again. In order to create the feedback loop, we need to store this matrix when it comes out from jit.gl. So let's create a new input. Let's call this velocity. By the way, this is position. Let's create another output. So the velocity here will be basically, let's do it like that, this number summed to the previous velocity, and then this value will be output as the new velocity. So this is now the new velocity. So this was the old velocity, and this will be the new velocity. Okay, so basically we sum together the velocity from the previous frame to the current number, and we get out the new velocity. And to store it, we set it inside this matrix. And you can see that now the particles start to accelerate indefinitely. Okay, in order to reset this process, we can clear those matrices. Let's clear all of them, and then the process will be reset. But let's start actually. Oh, yeah, sure. Let's do like this. Let's first clear and then bang again the JIT noise. You can see they're still pretty fast. So they continue to accelerate indefinitely because there is no attrition to that. In order to create some sort of attrition force, let's actually take the old velocity, multiply it by -1, multiply it actually again between some smaller number. Now let's actually first normalize it. So we get a vector that goes in the opposite direction of velocity. Let's multiply it for a number which is negative and small, and then we can sum it again to the velocity before applying it to to the position. So we are now having some sort of attrition force. The attrition force I think is too big. Let's make it a bit smaller. Exactly. Okay, so now we have some kind of attrition force which prevents the particles from accelerating indefinitely. Okay. Let's call this attrition. Now let's create another force to which the particles will be attracted instead of just going down because of gravity. So this, by the way, is gravity. Let's create another force to which the particles will be attracted. For example, we can use the mouse position as the point of attraction of these particles, so they will always be attracted to the mouse. And then, so the mouse will be the new attraction force. So in order to do that, let's get the mouse position inside the world coordinates. So first we need to send a window inside JIT world the message either mouse or mouse idle, I never remember. No, it's apparently idle mouse. Let's create a load bang. So now we get from here the position of the mouse every time it's on top of the jit.gl window. So we now need to get these coordinates. So this is mouse idle, I think. So we route this message and we get the coordinates of the mouse in window coordinates. So we need to translate this in world coordinates. So basically what we need to do is to divide these coordinates by the sides of the window. So let's basically create a message called getSize, which we will trigger periodically, like let's say every 2 seconds. So if you go full screen, for example, this will be updated. And then let's root out the size of the screen. So as we can see, these are the sizes. And then we need to divide the coordinates. Our mouse position for the sides. So we can use the vexpro object, which divides a list by another list. And now we have the coordinates in the range 0 to 1 on both the x and the y. But this is not enough, because when the x and the y are not on the same of the same sides, then the coordinates will be from 0 to 1, but this will not really be the same coordinates as in world coordinates. This because we need to account for the ratio of the window. So let's do something like this. Let's trigger this list a couple of times. And the first time we simply want to divide the two numbers by themselves, so the first by the second number, and this will be our ratio. So for example, in this case the ratio is 1.811, the ratio of the window. So what we need to do is to multiply this by 2. Let's use another vexpro object. We need to multiply this number by 2, subtract 1. So this is now the coordinates in the range -1 to 1. Exactly. Both in the y and in the x. And we need actually to unpack them to multiply the x for our ratio. And the y can be the same as before. So okay, now we can use this as our mouse position. So let's prepend mouse position. Let's actually put a 0 here. So this will be 3 coordinates in which we have x, y, and the mouse will always be centered in the world, so will always be at the position 0 in the z-axis. Then let's go inside jit.gen and let's create this parameter called mouse position. So it's a 3 vector parameter. So let's just set it by default to 0, 0, 0. And we can connect this value here. Can connect this prepend to jit.gen in order to get the mouse position. And now we can create a force using the mouse position and the original position. We can create a force that will give us a vector that points to the mouse position. So in order to do that, we have to do something like that. Let's put this a bit more to the right, all these guys. Okay, so let's get our mouse position. And let's subtract from the mouse position, let's subtract the original position. This gives us a vector that goes from the position of the particle to the mouse position. Let's normalize this vector, so we know that it always has a magnitude of 1. Let's multiply it for a really small number. This will be our force. So basically now we need to sum this force to the previous forces. So let's create another plus. This will be our new force. We sum it to the gravity force. And seems there is something. Oh, this also needs to be attached here. Oh, this force is anyway too big, first of all. The effort is pretty cool, but it's not exactly what I wanted. So let's see what is the problem here. Yeah, first of all, basically, let's just put a plus here, and let's put a minus here. So this will be more correct, because by now we were just subtracting, we were just repelling actually the particles from the mouse. So this should actually be a plus. We had to sum these forces together, and this should be a minus here. So let's see what is going on here now. Okay, so first of all, let's actually reverse the epsilon coordinate of the mouse. So let's multiply it by -1, because in a JIT world the epsilon coordinate is reversed in respect to how we calculated it. And let's use a sender, send mouse position with these 3 numbers, and let's create a receiver here instead of using a cable. So this makes a bit more clean the patch. So let's see what is the problem here. First of all, let's actually not normalize the attrition, and then let's multiply it for a bigger number, something like that. Let's actually also not include the gravity. Let's not include the gravity in this in the velocity that gets stored on frames by frames. And actually, let's copy this here. Actually, also the attrition should be subtracted, not to the initial thing. It's actually the same, but for correctness, let's subtract the attrition at the end of the sum of the forces. Okay, let's actually use the gravity simply after we store it inside the final force matrix. And let's see what we get here. It seems actually to work. Seems now it works. Let's make this force maybe a bit bigger. Okay. Yeah. So the particles are now attracted to the mouse. It's actually quite fast. I feel like this. I had to play around a bit with the parameters here. But one thing that we can do is to actually divide this the mouse attraction force by the length of the distance between the mouse and the particle. So we can do like this, get the length of this vector, actually take the power of this length, or even the cube of this length, and then I don't know, we can even multiply that by some number, for example 3, and then add 1 just to avoid multiplication by division by 0, and then we can divide that by that. And now our particles, the closer they are to the mouse, the more they will be attracted, and the farther, the less they will be attracted. So yeah, so now the effect is a bit more interesting. Okay, instead of using wrap, we can also use clip actually. So the particles will not bounce off will not go back on the other side, will simply just stay inside the boundaries of our cube, imaginary cube. Okay, so let's actually not create a cube but a rectangle. So let's actually create a sender of the ratio here of our window, and then let's create a receiver. Oops. And let's create a parameter ratio, and then we need to switch the single components of the position. And then we need to clip the x between minus ratio and ratio. So let's multiply this by -1. Let's delete the default numbers. Let's do like that. And then we can create a vector, 3 component vectors, which clips the epsilon, and then let's clip the epsilon and the z by -1 and 1. Okay, so actually the epsilon now will be clipped according to the ratio of our window. So yeah, that's a bit more correct. Can move with the camera around and yeah, have this kind of parallelepiped which contains our particles. So let's reduce a bit the attrition, and let's make maybe the gravity a bit bigger. Something like that. Let me reset the camera. Okay, so that looks cool. That looks good. Let's actually now create the lifetime of the particle. So let's create another matrix. Let's actually first create another noise. Let's actually first pack these guys into. Let's pack these guys into a subpatch and say like mouse pos and ratio. Let's pack this here. Okay, so now let's create a new matrix here. This will be the lifetime of our particles. Let's this is the initialization of the lifetime, and let's create a new matrix which we will simply call time. So old lifetime, because this is the lifetime that the particles have at the beginning of the frame. Let's create a new input here. So let's call this old lifetime. And then every frame, let's actually switch just one of these numbers. The first, because this is going anyway to be, let's put it to 1, but this is anyway going to be a 3-plane matrix. Let's actually create also another one here. This will be our feedback matrix. This will be the new lifetime of the matrices of the particles. So let's also create a new. Let's put this guy a bit away. Let's also create a new output. So new lifetime, and basically we have to subtract every frame to those particles a small quantity, for example 0.003. But we also need to wrap this number between 0 and 1. Now let's connect the matrix, the output to the matrix new lifetime. Okay, perfect. As you see, I also connected the metro here to the new matrix, because we need to bang it every frame. And let's see what we do with this number. Basically, we say if this number is less or equal than 0.0, then our particles will respawn at the original position. So let's create a sender. Is def. Oh no, actually is dead. Is dead. And then let's create a receiver here. Is dead. And let's say, let's bring this a bit on the right. Okay, let's bring also a bit on the right. So let's say if this particle is dead, then you should respawn to, let's say, the mouse position. So if this is false, then just keep going on your way. But if this is true, then respawn on the mouse position. So let's see how this works. Yeah, let's load bank. Okay. And so let's see. Yeah, seems to be working. So it seems to be working. Let's make it a bit more interesting by setting the blend enable for the jit.gl mesh, blend add. Depth enable, let's set it to 0. And let's also send it a color, which is based on the lifetime of the particles. So for example, out for color. Let's actually use a mix object. And let's use the lifetime as the mixer parameter. And let's mix, for example, a vector slightly red. So when this is 0, and when they start, let's make them white. So when the particles are fresh created, they will be white. And then when they are going to die, they will be red. So let's see. Okay, yeah, seems to be working. Now it's a bit too two-dimensional. So let's actually create the gravity. Let's actually put it also that goes a bit in the z-axis. We can use, for example, we can use the mass, for example, to set. Oh, let's actually create a new input. Let's actually create a new input and let's create a new noise. But it's not light time, but lifetime. Let's create a new noise that will be our Z attraction. So Z attraction or Z gravity, if you prefer. And then we can use, this is just one plane, yeah. We don't need more planes. Let's use just one. And then we can use these. Let's switch x. And then let's say multiply this by 2. And then we subtract 1. And then we multiply that by a small number, like for example 0.05. Let's touch to the Z. And let's bang it. And now it's a bit more three-dimensional, I will say. Let's play a bit around with the forces parameters here. What do we have? Oh, this is wrong. This should be on the z-axis. Let's actually make it also like 0.05. Okay, and let's make, I don't know, 0.04 here. Okay, so now, yeah, so now the particles will respawn to the mouse position when they die. Otherwise, they will kind of lie on the floor because they are too far to be attracted from the mouse. Seems about right. Makes also the attrition a bit smaller. Okay, so yeah, that's it. Can also make this a bit bigger. I don't know, can play a bit around with the parameters, but the basic mechanics are implemented. So yeah, that's our emitter. Emitting particles, when they die, they just disappear. And this is maybe it's a good starting point for you to experiment with your own emitter code. Maybe also make it a bit smaller so the particles live longer. And you can also tie all these parameters to some external input to what you want, basically. So, cool. I think that's it for this tutorial. Thank you for watching. And you can download the patch on my Patreon. And if you want also to get some more cool patches, you can also become a Patreon of mine, join my Patreons, and get access to a wide number of visual patches. So, okay, thank you, and see you on the next video. Ciao, ciao.